Okay, this is section 3.2, polynomial functions and graph characteristics. So this is going to be all of our graphing characteristics about these polynomials. Some of them we have done before. We did them with quadratics. Others will be new for today. But before we get to that, we've got to talk just a little bit more about what a polynomial function means and a little bit more about our degree and what we call the leading coefficient, because we use all that stuff to graph. So a polynomial function is a function of the form, and this is a lot in this box, but don't be overwhelmed by the notation in this box. The notation in this box, a sub n, is just a leading coefficient, like an integer, okay? And then it's x to the n, which means it could be like x to the third or x to the fifth or something like that. So it looks like a lot. Don't let this overwhelm you. It's really no big deal. It just says the coefficients, a sub n minus 1, a sub 1, etc., are real numbers. A sub n does not equal 0, and n is a positive integer, okay? And we're not going to have any negative exponents in these things at all. A polynomial function is not going to have any negative exponents in it. It's not going to turn it into what would be a rational, right? This number out in the front, though, the one in the very, very first with the highest degree, is called the leading coefficient. And we'll talk a lot about the leading coefficient. We already have. We just called it A. In our parabolas, in our quadratics unit, we just kept calling it A, but A was always our leading coefficient. All right, so as I go down through each one of these, I want to give their number of their degree, and then I want to list their leading coefficient because there's a big difference. Sometimes I think this is easier to start at the bottom and work our way up. So like for this very bottom one, what is the degree of this term? Not by name, but by number. 5, because that's the biggest exponent we see. Remember, that would be called quintic if I was to call it by name. It's degree 5. And then what do you guys think would be the leading coefficient here? The 9. Good. Yeah, the number out in the very front. Okay. So the 5 is the degree because that's your biggest exponent. The 9 is your leading coefficient. So in this one, this is degree 4. It's called quartic. And what's my leading coefficient here? -3. Okay, it's the number in the very front. It is the -3. Okay, working our way up. This one is cubic, degree 3. What's my leading coefficient here? Good, -1. And this is our quadratic, degree 2. That's the biggest exponent. Leading coefficient, 12. This one is degree 1. Remember, this x has a 1 right there. We just don't put it. It's called linear, degree 1. This would graph a line. We know that. My leading coefficient is the -5. And as to not be confusing and having started with this one, what's my degree here? 0. Good. Yeah, this one is a constant, right? It doesn't have a degree with it. It's of degree 0. And your leading coefficient is just the 4. All right, we're going to do a little reminder of the parent functions. Okay, start with the polynomial parent functions. These are all on our wall over there. The constant function, though, we haven't really talked about what that actually looks like, calling it the constant, but it's the horizontal line. Okay, so my constant function, f of x equals c, that's our horizontal line. If y equals just a plain number, it's going to be a horizontal line. Linear, we know what this looks like. F of x equals x. So this is the parent function of a line. Y equals x, 1, 1, 2, 2, 3, 3. Quadratic, we know what it looks like. It's our parabola, and this is what the parent function looks like. F of x equals x squared. We know that this is like over 1 up 1, over 2 up 4, over 3 up 9 because I'm squaring my x every time. Negative 1, 1, negative 2, 4, negative 3, 9. All right, we did these back in Unit 1, but we'll remind ourselves now the cubic function. F of x equals x to the third. And this is the one that kind of looks like a vertical snake. Okay, so it starts up this way, and it comes right across at 0, 0, and then goes down in quadrant 3. It's in quadrants 1 and 3. Okay, let's go ahead and do what quartic and quintic look like. Our quartic function, we know, would be f of x equals x to the fourth because it has to be raised to the fourth power. And guys, if we graph something that looks to the fourth power, it looks a lot like the parabola. It's just a little bit more stretched out. So it looks a lot like a parabola. Because they're both of even degree, because the parabola is x squared and this one's x to the fourth, they both look like this. And similarly, since our quintic one is of odd degree, f of x equals x to the fifth, that's what quintic means, to the fifth power, it's going to look a lot like our x to the third, only a little bit more stretched out. So it's like, it looks like the vertical snake, only it's just kind of been stretched out a little farther. So it kind of looks like this. This one looks like kind of a fatter parabola, and this one looks like a more stretched out of our x to the third snake. And that just keeps happening. If it's an x to the sixth, it's just going to be stretched out a little bit more this direction because it's an even degree. If this one was an x to the seventh, it would still be in quadrants 1 and 3 and kind of stretched out a little further. So let's talk about that, both of them facing the same direction or them facing opposite directions, okay? It says, using your graphing calculator, determine the end behavior of the following functions. But we're not going to use our calculator. We don't have to. End behavior. This is something new today, but something we're going to talk about all year long. End behavior is asking you, what is the graph doing at the arrows on the ends? End behavior. So what's the graph doing at the arrows on the ends? Which direction is it pointing? What's it pointing at or pointing towards? So I'll put over here, what is the function doing at the arrows on each end? Hence why we call it end behavior. So we're going to draw a conclusion right now that I know you all can make. If I have a parabola, okay, I have a parabola, and it's got a positive a, it's going to look like this, right? Both ends pointing up to what? What are these guys pointing up to? Positive infinity, okay? What if I have a parabola and the a is negative? Then what do both ends point to? Negative infinity, right? Because it points down, okay? And a parabola is an x squared, right? Okay. So it's an even exponent, right? Even exponent. So what about just x all by itself? Our line. It goes like this, right? Just linear, just a line. So on the left, on the right-hand side, what are we pointing at? Positive infinity. And on the left-hand side, what are we pointing at? Negative infinity. Well, what if this is positive x squared, this is negative x squared, this is positive x. What about negative x? What does that do to my line? Do you guys remember? It just flips it, right? This way. which means I'm going on the left-hand side to positive infinity and on the right-hand side to negative infinity. So this is the end behaviors that we're talking about. So right here, if it's even, they're both going to go up or they're both going to go down. If it's odd, they're going to go in opposite directions. So you already know this information. You just have to think about whether it's a parabola or a line. Now look, this is also an odd one, right? See how we're up on the right and down on the left? Because it's odd. Every odd function that has an odd exponent will do that. And every even one, they'll both go the same direction. So let's fill out this chart. If I have a positive leading coefficient, okay, positive, and I'm even degree, like my parabola right here, positive and even, okay, then it looks like this. It goes up to infinity on both ends. And if I'm an even degree and I'm a negative leading coefficient, then I go down on both ends. To negative infinity. This is like our parabola. If I'm an even degree, if my degree is a 2, a 4, a 6, an 8, a 10, any even number, I'm either going to go up if it's a positive leading coefficient, or I'm going to go down if it's a negative leading coefficient. And you guys already know that. I asked you a million times in Unit 2, does this parabola open up or down? Does this parabola open up or down? Does this parabola open up or down? And we looked at that A, that leading coefficient. All right, so if we're of odd degree, it's going to be like the line, okay? Odd and positive, we're going to go up on the right and down on the left to negative infinity. And if it's a negative leading coefficient, we're swapped. We're up on the left to positive infinity and down on the right to negative infinity. Okay, so this one is, when I look at this guy, my words should go even degree, because it's a 4, even, and positive leading coefficient. So even, positive. So even means it's going to go the same direction on both ends. Positive means they're both going to go up to positive infinity. So even, positive, they both go to positive infinity. Let's talk about this notation. I'm going to read this to you. This is a math sentence. This says, as x approaches infinity. So what's that saying? That's saying as my x's are getting bigger, look here at my picture. As my x's are getting bigger, as x approaches infinity, f of x, which I can always replace with a y, my y values are also approaching infinity. As my x's are getting bigger, so are my y's. And then the other statement says, as x approaches negative infinity, so as I go back to the left, my y values are also approaching positive infinity. This is an x to the 4th, so that's why I'm pointing up at this one with the positive leading coefficient. So this arrow, when you read this, approaches. Okay, that's what that arrow is saying. As x approaches infinity, y approaches, and as x approaches negative infinity. My brain sometimes goes, as x approaches infinity. That means as x goes to the right, or as x goes to the left. Negative infinity means x to the left. All right, number 2, I'm even, which means they're both going to go the same direction, but I'm negative. So even, negative, which way do they both go? It's like the upside down parabola, guys. Even exponent, but negative leading coefficient. Which way do they both go? Down. Negative infinity. As x goes to the right, the y's go down. As x goes to the left, the y's go down. Okay, this one is odd. So we're going to have one positive and one negative. And we're odd positive. Okay, so that means on the right, Okay, odd positive is like our line, or like this guy right here. This guy's odd positive. So he goes up on the right and down on the left. So as I go to the right, I go to positive infinity, and as I go to the left, I go to negative infinity. All right, here we're odd negative, odd exponent. 3 is odd. Leading coefficient is negative. So this is going to go the opposite direction. As I go to the right, I'm going down. As I go to the left, I'm going up. This is just a quadratic. This is a parabola. We're even, but we're negative. I could have asked you this before I ever even started this. This is a parabola, and which way does it face? Down, because of the negative 2. Even and negative. They both face to negative infinity. This guy is odd, okay? Odd, positive. Odd positive means as I go to the right, I go up. As I go to the left, I go down. All right, we already filled that chart in, so come down here. This says determine the sign of the leading coefficient and whether the function is of even or odd degree. So I just want to look at this one, and I want to figure out, first of all, is it even or odd? Are they going the same direction or opposite directions? They're going the same, so it's even. And is my leading coefficient positive or negative? Negative, because they're both going down. For this guy, is number 8 even or odd? Definitely odd, because we're going opposite directions. Odd ones go opposite directions. And is my leading coefficient positive or negative? Positive, because I'm up on the right. Good. All right, so that's end behavior. Okay, that's end behavior. Let's talk about turning points and max and min and increasing and decreasing now. Okay, the point at which a polynomial function switches direction is called the turning point, right? So the polynomial, it comes up and it changes direction and it goes down and then it goes up and then it changes direction, it goes back up again. Those are called the turning point. The turning point is higher, if the turning point is higher than any nearby point, it's called a relative maximum. This guy right here, this is a relative maximum. And I'm just going to write rel max so I save myself some space. That is a relative maximum. Anybody have any ideas about why it might be called the relative maximum? Like, that seems weird that we're putting that extra word in there. It's not the actual max. Ooh, I love that. What's the actual maximum of this graph? Positive infinity, right? Because this guy is going all the way up to positive infinity. Guys, that's called the absolute maximum. Okay, the absolute maximum is positive infinity because this guy is pointing all the way up. This point in the middle that looks like it's a hill on the graph is called a relative maximum because it is the highest value if I'm just looking like within this little range of the graph right here. All right, this guy down here then, we're going to call it the relative minimum because it's a lowest point in that area. This is a relative minimum. And sometimes, oh, by the way, our absolute minimum is negative infinity because this side's pointing down to negative infinity. So the difference between relative and absolute, okay, is the absolute max and min are a lot of times with these guys, positive infinity and negative infinity. So we're looking for the relative max and mins. All of these maximum and minimum values together are called the extrema. So if you're asked to find the extrema, you're being asked to find the maximums and minimums. Relative max, relative min, absolute max, and absolute min. All right. So the other part that we're going to talk about right here are called the intervals where the graph is increasing or decreasing. Okay? And those spots are defined by the turning points. All right, and here's what I like to do with increasing and decreasing, you guys. I like to pretend that there's a Hot Wheels car sitting on this graph. Okay? A Hot Wheels car sitting on this graph. Can you picture a car sitting right here with me? And if there's a car sitting on this graph right here, from negative infinity, right? Because isn't this back here at negative infinity? All the way to this interval in this range right here between these two spots, because remember this goes on forever, right? Down here. Is my car driving uphill or is my car driving downhill? If I'm a Hot Wheels car driving right here, I'm going up, right? So from negative infinity to whatever this turning point is, I'm increasing. Okay, then I get to the top of the hill, and what happens to my car? I start doing what? Going downhill. So then I'm decreasing in this interval right here. I'm decreasing in this span of numbers. From this turning point to this turning point, I'm decreasing. Then I get to this turning point, and from here all the way to positive infinity, because that's where this is pointing to, what am I doing? What's my car doing? Am I going up or down? I'm increasing. I'm going up. My little car is going back up again. All right. So that's what it's called. Now, the only thing about this is when you're listing out these spots, like this one goes negative infinity to, you use the X value. Okay. So if this is like negative 2, you'd say from negative infinity to negative 2, we're increasing. And then you're going to go negative 2 to 3, you're decreasing. And then we're going to go 3 to positive infinity, I'm increasing again. You use the X values. Let's write that down. For increasing and decreasing, use X values only. Use your X values only. Okay, so graph this function with me in your calculators. Okay, so it says find the turning points of the function f of x equals x cubed. So let's go to our y equals and type in x to the third minus 6x squared plus 7x plus 2. Here's our graph. Okay, here's our graph. Okay, it says use the calc menu to find your maximum and minimum values. So I can see my relative maximum is right here and my relative minimum is right down here. Okay, the calculator calculates these for us. We just have to do the whole left bound, right bound thing so it knows which section of the graph I want you to find the maximum in. So I'm going to go to second calc, and I want to find my relative maximum first. Okay, I'm going to fill in this spot right here. So I'm going to go down to maximum. I went to second trace, which is calculate. I'm going to go down to maximum. Now there's a little flashing spider. It needs to be on the left side. See where it says right here, left bound, down in the bottom corner of the screen? you need to be on the left side of your maximum. So I'm on the left side. If you're not, you use your arrows and move it around, but you need to be on the left side of your maximum and hit enter. Then it changes it to right bound. So then you move to the other side of the hill and you hit enter. Now it shows you, okay, it says, okay, you gave me this barrier right here. Between these two lines that I just made on the graph, you're wanting me to tell you what the highest point is? Why, yes, I am. That's exactly what I'm wanting you to do. So now it says guess. So now it wants me to put my little cursor on what I think is the maximum and hit enter. And then it gives you your maximum value. So we'll go to 2 decimal places. And so I want you to consistently do that. Let's always round these right now to the nearest hundredth, which is 2 decimal places. So the 3rd decimal place determines my rounding. So my maximum value here is 0.709. So the 9 causes the 0 to go up to a 1. And 4.303. So it'd just be 30. Now for my relative minimum, that's this lowest point down here. So I'm going to do it again. I'm going to go to second trace, which is calculate. And I'm going to tell this thing that I need you to calculate the minimum for me. So now it wants the left bound. The calculator tells you exactly what it wants you to do. It wants you to go to the left side of the minimum, which is going to be on this side. So I'm going to move my little cursor just a little bit closer. And now go to the right bound. It tells you right bound. So move over to the right side, move your little cursor. So you're on the right-hand side, hit enter. So now the calculator is saying, okay, between those 2 lines that it just formed on there, you're wanting me to tell you what the lowest point is. You're asking me for the minimum. Calculate the minimum between those 2 boundaries. Yes, that's what I want. So take a guess. Hit enter, and it gives me the minimum. And I'm going to go to 2 decimal places. So it says 290. So I can just say 29. And negative 4.30. Okay, right now we're going to go to 2 decimals. And I want you to do that on the homework as well, and on quizzes and on tests. We're going to stick with 2 decimals right now. All right, so let's talk about the increasing intervals. Okay, and I always look like I'm reading a book. I always go from left to right. Okay, so looking from left to right. The leftmost, and remember, you got to chunk this thing off like I did up here. You got to have a chunk and a chunk and a chunk. All right. So every chunk has to have an end and a starting and an ending. Okay. So for my increasing intervals, from negative infinity all the way up to whatever my x coordinate was right there at my maximum. So negative infinity all the way to 0.71, I'm increasing. Because that's that point right there, and I use x values. So it's right here. Here's my x value. Then from 0.71, which is my x value, all the way up to 3.29, I'm decreasing. My car is going downhill. I'm using x values. Underline them, highlight them, do whatever you need to do to them. So those are the ones you use for increasing and decreasing. Okay, and then at 3.29, all the way to positive infinity, I'm increasing again. So I have 2 places where my car is going uphill and 1 place where my car is going downhill. Okay, let's graph this guy and fill in some of these this information over here. Okay, so go back to your y equals, clear this guy out, and do negative. And remember, when you type in this minus sign right here, you have to use the negative sign that's in the very bottom row, not the subtraction sign. Negative x to the third plus 3x squared. All right, here's what mine looks like. Is this guy even or odd? Odd. And is it a positive or negative leading coefficient? Odd, negative. Is it acting like we thought odd, negative should? Odd means it's going opposite directions. Negative means it's going up on the left and down on the right. So I can already fill in my in behaviors. As my x's are going to the right, I'm going down to negative infinity. As my x's are going to the left, I'm going up to positive infinity. Okay? Let's get our turning points. Let's get our relative minimum. Where does it look like our relative minimum is here? Looks to me like it's at 0. Let's calculate it. Relative minimum. I'm going to calculate my minimum. I'm going to go to the left. I'm going to go to the right. And I'm going to take a guess. And says my minimum. Oh my gosh. Okay, look at these numbers, you guys. I'm glad that it did this so we could talk about it. Do you see these numbers? Do you see how it says this e to the? Did you guys just do that too? No? What did yours tell you? 0, 0. Good. Okay, so when it says e to the negative 6 like this, that means that this point is in scientific notation and it's 0.000000146. This one is 0.000000000000693. So the calculator just does an error a little bit, but these are, if I'm rounding to 2 decimal places, these are absolutely zeros. Okay, these are 0 and 0. This e to the negative 6 means a tiny itty bitty number. E to the negative 12 means a tiny itty bitty number. So it is definitely at 0, 0. So my relative, that's my minimum, 0, 0. I'm going to put a point there. It's absolutely a point on my graph. Okay, let's calculate my maximum now. It looks like it's right here, but let's calculate it. Second calc. Oh, no, that's not what I wanted to do. Maximum. Left bound. Right bound. Guess. 1.99999999997. I'm just going to go ahead and make that be 2 because that's what it would round up to if I'm going to 2 decimal places. 2, 4. So that's easy. My max is at 2, 4. Over 2, up 1, 2, 3, 4. And I'm coming down this way, and I'm turning, and I'm going up, and I'm turning, and then I'm going back down this way. What's the domain of this graph? What are the x values that are included in this graph? Is there anywhere that there's not going to be an x value? Do you think it's everything?
Yes.
Yeah, I think it is, because I think this is going to keep going this way forever, and I think this is going to keep going this way forever. So I think our domain is going to be negative infinity to positive infinity. How about our range? Any y values not included? Some places there's 2 y values, right, in here? I think it's everything again. That's easy. All right, let's do increasing and decreasing intervals. When I do increasing and decreasing intervals, I like to separate it out. So I've got negative infinity to my first turning point. Then I go to my next turning point, and then it goes to positive infinity. So in this span right here, from negative infinity to 0, which way is my car going?
Up.
Really? Right here?
Oh,
If
yeah.
you were a car driving on this, which way would you be going? Downhill. I think we're decreasing. So negative infinity to 0, I'm decreasing. And then how about 0 to 2? Remember, I'm only using the x values. I don't care what the y is. I'm only using the x. How about 0 to 2? What's my car doing? Increasing. I'm definitely going uphill. And then this is 2 to positive infinity because it's ending. It's positive infinity out here, guys. Don't put negative infinity. That's end behavior. That's different. Okay? This is actually going out to positive infinity. It goes negative infinity, turning point, positive infinity every time. So in this span right here, from 2 to positive infinity, which way is my graph going? Which way is my car going to be driving? Downhill or uphill? Downhill. So I'm decreasing from 2 to positive infinity. All right, we're going to take a 2-minute break. 1. All right. So zeros, we already know what zeros are. Zeros are the point at which the function intersects where? X-axis. Good. X-axis. That's right. Remember, we call them the zeros, the roots, the intercepts, x-intercepts, the solutions, whatever you want to call them. That's what they all are, okay? And a polynomial function of degree n can have at most n real zeros. If it's degree 2, it's not going to have more than 2 zeros. If it's degree 5, it's not going to have more than 5, okay? And an even degree polynomial is going to have an even number of zeros. And an odd degree polynomial has an odd number of zeros. So we're going to graph this first one in our calculators and see if we can identify the zeros. So go to y equals, type in x to the third plus x squared minus 2x see if you can identify the zeros. You can see them on the graph. Let's see them let's look and see if we can see them in the table. If I'm looking in the table, what am I looking for in the table? What tells me where the zeros are? Where the y is a 0. Good. And this is an x to the third. So how many might there possibly be? 3. Okay. Since this is an x to the third, there might be 3. Are there 3? Are there 3 places where this guy crosses the x-axis? Yes. And I can see them really nicely in my table. -2, 0, 0, 0, and 1, 0. I can put them on my graph. I don't have my max and min identified right now, and that's not what we're doing right this second, so I'm not going to worry about identifying them right now. We'll do all that together, but I definitely see that this guy comes like this, and I can make a nice sketch. I am odd positive, so my end behavior is up on the right, down on the left. That's exactly what it's doing. And these are my zeros. You could also list them, x equals -2, 0, and 1. Again, I don't care if you write them as x-intercepts or if you write them as zeros like this. Do not put them listed like this in parentheses. All right, let's see if we can find the zeros in number 2. Number 2 is even or odd? Even. It's x to the 4th. So how many zeros am I maybe going to have? How many zeros? 4 or less. Okay, this guy's even. And what's my leading coefficient? Is it positive or negative? Negative. So if I'm even negative, this guy better be facing down on both ends when I go to graph it. Let's check and see if we can see 4 zeros and if I can find them in my table or if I'm going to have to search for them. Okay, -x to the 4th plus 4x to the 3rd minus 2x squared minus 4x plus 3. Okay. All right. So this guy looks like kind of like an M, right? So I think I can see them. How many times does it look like this guy crosses the x-axis? 3. But instead of crossing one time, what does it do? This isn't crossing. What's this doing? Bouncing like a ball? It's not crossing right here, guys. It's bouncing. Do you see how it's not going across the x-axis? It's bouncing on it. All right, let's see if we can go to our table and identify these guys. Looks like negative 1, 0, 1, 0, and 3, 0. Negative 1, 0, 1, 0, 3, 0. And if I'm just doing a nice sketch, okay, I'm not worried about my max and mins right now. I'm just worried about my zeros for this little part. We'll put it all together here in a minute. Coming up, bouncing here, up and back down. So my behavior is acting just like I knew it would. Even and negative means they're both going to go the same direction, and it's negative, so they're both going to go down. I'm bouncing right here. I thought I was going to get 4 zeros. I only got 3. Do you remember why? I told you why. Remember why? What is happening at 1? It's bouncing like a ball. And when it bounces like a ball like that, it's called having a multiplicity of 2. It means it's happening twice. When it bounces, that means that it's actually happening 2 times. It's not crossing, it's bouncing. It's called having a multiplicity of 2, and we're getting ready to write all of that down. That's what it looks like graphically. Let's see what it looks like algebraically. This says the linear factors of a polynomial can reveal its zeros. Linear factors can be found by writing the polynomial in factored form. We already know that. We know that when we factor something, we can set each of the factors equal to 0 and find the zeros. So I'm going to go to factor this guy. Anytime I go to factor, what's the very first thing I look for? GCF. Good. Does it have one? I see one. Take out an x, leaving me x squared minus 2x minus 15. Then this guy, left in the parentheses, is a trinomial, not a perfect square. A is a 1, so I can use my shortcut. 2 numbers that multiply to negative 15 and add to negative 2, negative 5, and positive 3. Now, to find my zeros, remember at this stage, you set each piece equal to 0. So x equals 0. X minus 5 equals 0, so x equals 5. X plus 3 equals 0, so x equals negative 3. Guys, this was an x to the third. If it's an x to the third, how many zeros should I get? 3. How many did I get? 3. I got a 0, a 5, and a negative 3. Cool. Just by factoring it, we can find them. We already know that. This is exactly like what we did with quadratic, only we added one more 0 in there. No big deal. All right, let's talk about this one. With the multiplicity of a 0 is equal to the number of times the linear factor occurs. So let's look what happens with multiplicities when I do it linear. So write this in factored form. We know how to do that. Take out the GCF, which is an x, leaving me x squared minus 6x plus 9. So now look at this guy left over. Trinomial, and it's a perfect square trinomial because 9 is a perfect square, x is a perfect square, x minus 3 squared. So if I'm trying to find my zeros now, I get one of them's at 0. Where are the other two at? The other two are at 3. And it happens twice because it's x minus 3 times x minus 3. So to get my zeros here, what are the zeros and their multiplicity? Well, x equals 0, it only has a multiplicity of 1. It only happened one time. But x equals 3 has a multiplicity of 2 because it happens 2 times. It's x minus 3 and x minus 3 twice. So I'm going to get it 2 times. The graph is going to bounce there instead of cross. So this is the same graph here. It's odd and has a positive leading coefficient. 0, 0, 3, 0. So if it's odd positive, I have to go up on this end. I bounce here because 3 happens twice. I must come up here and cross back down. At 0, 0, there's a multiplicity of 1. And at 3, 0, there's a multiplicity of 2 because it bounces. If the multiplicity is odd, the graph crosses at that 0. If the multiplicity is even, like 2, or maybe it was a 4 or a 6 or an 8, if it's even, it's going to bounce like a ball at that 0. So looking at this table right here, I'm supposed to figure out my zeros, list their multiplicities, and effect means does it cross or bounce. So x plus 7 equals 0. So my 0 is negative 7. The degree is 2 right here, so that's its multiplicity. And if it's an even multiplicity, it's going to bounce. Okay, 2x plus 1 equals 0. So 2x equals negative 1. X equals negative 1/2. That's my 0. It's only happening once, which means the graph crosses at that spot because 1 is an odd number. X minus 4 equals 0. So x equals 4 is my other 0. Its multiplicity is 3. It happens 3 times. 3 is an odd number, and if it's odd, it crosses. All right, this one is not factored for me. I'm going to have to factor it first. No problem. Take out a GCF, which I see is going to be x squared, leaving me x squared minus 2x minus 8. I'm going to check my leftover trinomial. It's not a perfect square, but I can check for shortcut. Two numbers that multiply to negative 8 and add to negative 2. That's definitely negative 4 and positive 2. So my zeros, well, I need to set this guy equal to 0. X squared equals 0. I know how to solve something that says x squared equals 0. I just take the square root of both sides. 0 can't be positive or negative. So it's a 0, but what's the multiplicity here? How many times? Yeah, it's 2. It definitely happened twice, which means it bounces. X minus 4 equals 0. So x equals 4. That one's only happening one time, so we cross. And x plus 2 equals 0. So x equals negative 2 for a 0. It only happens one time, so it crosses. Okay, we're going to put all this together now. We're going to put all this together. We're going to graph this. We're going to find the zeros and all the things, okay? This is what we're going to do. So get your calculator. Type this guy in. X to the 4th. X to the 3rd. Minus 4x squared plus 5. All right. Let's get some information down here. First of all, is this guy even or odd? Even, right? And is my leading coefficient positive or negative? Positive. If I'm even positive, both of my end behaviors should be going up to what? Positive infinity. Let's get that filled in right off the bat. As my x approaches positive infinity, as my x's get bigger, my y's go up to positive infinity. As my x approaches negative infinity, my y's also go up to positive infinity. Good deal. Okay, so we got that part done. All right, I think I need to work on my relative max and mins and kind of get some stuff on my graph. See if I can get some zeros or get my relative max and mins, have my calculator calculate something for me here. Let's see. Let's go to the table and see if I can see anything pretty in the table at all. I mean, it looks like 0, 5 is not bad. I could put 0, 5 on my graph. Negative 1, 1. That's a point. 1, 3. Those don't look like special points, but they're points. I can't see any of my zeros just with my integers here. So it looks like negative 2, negative 3. Looks like I'm going to have to do some calculating. Okay, that 0, 5, it does look like a turning point though. What does 0, 5 look like right here? What would I call that? A maximum, right? The relative maximum. And yes, it is also the y-intercept, but it's certainly going to be a relative max. It's a bump. So we can go ahead and put 0, 5 in our relative maximum. How many relative minimums do I have? 2. Okay. Hey guys, something else cool about turning points. The number of turning points on your graph is always going to be 1 less than the degree. So like, what's my degree here? 4. So I'm going to have 4 zeros, the possibility of 4 zeros, but my turning points are going to be 3. The number of turning points is always 1 less than your degree, always. So if you're degree 5, it's going to have 4 turning points. Degree 6 is going to have 5 turning points. All right. I'm going to work on this guy right down here. I'm going to work on this relative minimum right down here. So second calc, minimum. I got to go to the left side, so I got to move my spider. I got to go to the right side, move my spider. I got to take a guess. Looks like my relative minimum, one of them, there's 2 of them, but my first one is at, I'm going to go to 2 decimal places. We're going to do that every time. 2 decimal places. Negative 1.8, and then it's 3.8, which makes the 3 go up to a 4. And then negative 3.309, so that makes the 9 makes the 0 go up to a 1. Use your proper rounding rules. You look at the third number over to determine what the second number is going to do. Okay, so negative 1.84, I can't get it exact, but I can get really close. Negative 1.84 is almost to negative 2, and then negative 3.31. So negative, almost to negative 2, and then negative 3, 1, 2, 3.31. Looks like right there. So I'm getting some nice information here. Okay, so let's get our other relative minimum. Okay, let's get our other relative minimum. So second calc min. I'm going to go to the left side of it. I'm going to get really close up here to it. Left. And then I'm going to go over to the right. And then I'm going to calculate it. Oh, take a guess. Okay, so my other one is at 1.088, which means 1.09. And then 2.954, so 2.95. Okay, 1.09 and 2.95. So let's graph that one. 1.09 and 2.95 is almost to 3. Okay, and I can keep glancing at my graph. I can definitely graph this now. I certainly have enough information in my turning points. I know this comes down like this. Oh, wait a minute. I better get my zeros. This one crosses the x-axis. This is a 0 right back here. I better get that 0. So second, calculate 0. Oh, I got to come all the way over here. Left side of that 0. Okay, left side of that 0. Right side of that 0. Guess the 0. All right, it's right at 0, so negative 2.32, 0, negative 212.32. Okay, then there's another one. Second, calculate my 0. I did this in a whole video back in section 2.4. Left side, right side, guess, and I get negative 1.4114, negative 1.140. So right here. Ooh, look at all these dots I get to connect. All right, connect the dots here and back up and around to here and back up and around to here. Whew. I might have got a little carried away over here. This probably should have went up a little better, but that's all right. It's a nice sketch. All right, so I only got 2 out of 4 zeros. What does that mean about the other 2 zeros? They're what? There's 2 more, but what are they? How come I can't see them? They're imaginary, guys. I can't see the other 2 because they're imaginary. If I were to solve this thing algebraically, which we'll do later, we're going to find that they are algebraic. So, Evelyn, I'll show you in a minute, okay? The zeros. I'll show you in a minute. Okay, so let's do domain and range. X values included in this graph. Remember, this one goes forever in this direction. This one goes forever in this direction. So I'm going to say domain is all real numbers. My range, however, though, is not all real numbers, because if I'm looking at the span of the y's, down at negative infinity, there are no y values. Okay, this guy goes up on both ends. So I need the smallest y value up to the biggest y value. Well, the smallest y value is certainly at this minimum right here. And I found it. Okay, it's right here. So negative 3.31 included all the way to positive infinity. These turning points are super important to find because they give us all kinds of information. Now let's do increasing and decreasing intervals. And here's what I like to do on increasing and decreasing, guys. I like to divvy it out based off of my turning points. So there, to there, to there, to there, and then positive infinity. So my turning points, remember, I only worry about the x's, okay? I'm only worried about the x's. So come over there and highlight them even over there if you need to. I'm only worried about the x's. So my x's, this is negative infinity. This first turning point right here, this one was at negative 1.84. Then my next turning point is at 0. That's that one. Then my next one is at 1.09. And then this is positive infinity. I like to do this because now as I go to write my increasing and decreasing intervals, I can see the exact numbers that I'm dealing with for each section I'm sectioning this off in. So in this first section, from negative infinity to negative 1.84, my car is driving downhill. So that's decreasing. So negative infinity to negative 1.84. Then in my next section in here, my car turns and starts going uphill. So I've got my numbers up here. It makes it super easy for me to go negative 1.84 to 0. Then in my next little section right here, this guy right here, I'm going downhill from 0. Oh, decreasing. Sorry, started putting it in the wrong spot. 0 all the way to 1.09. And then starting at 1.09 and going all the way out to positive infinity, I'm increasing again. So you only use the x values, okay? Sometimes I really do like to just go over here and highlight these x values or write them across the top like this so that you're just looking at each section like that, okay? All right, we will finish these other two probably together on Tuesday. And let me get your homework assignment.